In this video, we will be discussing the properties of liquid and how it behaves in different situations, as well as some basic properties of liquid and the motion of fluid. So typically when we talk about motion of fluid, we are usually looking at the motion of fluid through pipes. So there's some important things to consider. There is this equation that we will use to describe the pressure. And this is the vertical motion of fluid. So this is vertical. Right, so we have our initial pressure plus our mass per unit volume, also known as our density, times our gravity, so our gravitational force that's causing the liquid to move downwards, as well as the height of the pipe. Right, so where our pressure knot is represented by the pressure of the fluid when it enters the column, height is the height of the column, fluid density is represented by rho, and we are usually solving for this pressure at the end. So we can use this pressure to find the different variables for a situation like this. So when we talk about shear stress of a liquid, so think about if you were to push different kinds of fluids. So if you were to take really thick honey, and if you were to take like a popsicle stick and skim it across the surface, right? You'd notice that there'd be some resistance, right? There'd be some force and there'd be some stress developed because of the viscosity of the fluid. Whereas if you did that with water, it would have much less pushback. So these are some properties that we use to describe liquids. So forces that act on the surface of a body of fluid can be expressed in terms of normal and tangential components. So the normal component we represent with pressure times area, and it's acting normal to the surface, so perpendicular to the surface of the fluid, and the tangential component is acting tangent to the surface, right? So right across the surface with the equation tau times area. So where area is the surface area of the surface that we are acting upon, this symbol tau is for shear stress. Right, so we're going to talk a little bit more about shear stress, and shear stress is represented by F tangential divided by A, which comes from this equation here. So the viscosity of a fluid are the internal properties that cause resistance in the fluid's motion. So if you think about things that are more viscous, so the more viscosity a fluid has, the has less of a tendency to be displaced, so it has more of a tendency to remain in its shape. So using our previous description, this is like honey, this is like a cornstarch slurry, for example, or a milkshake, right? Those have high viscosity because you can't displace it as easily, right? So if you were to take a jar of really thick honey, turn it upside down, turn it back right side up, you might notice that it might not move at all. If you did that with water, that would not work. So water, alcohol, and oil have much lower viscosity compared to our other examples. So it's an internal property, so there's a lot of different equations that we have going on. So it's represented with this model here. So by no slip conditions, the velocity of the top layer is equal to u, right? So that is this long arm here. And the velocity of the bottom layer is equal to 0. And that is this point here. Okay, so where our velocity is a function of y, we have uy over L, which is the length of this part of the triangle here, as a function of y. And we represent this property called shear rate with this equation here. This is the behavior of fluid between two parallel plates, where our shear stress, tau, is our force, so our tangent force, which acts here, right? So that's perpendicular to where our maximum velocity is. And A is the contact area between the plate and the fluid. So For many fluids, we're using shear stress times alpha and, for many fluids, tau alpha du dy. So tau is equal to our viscosity times our shear rate. So this is and our viscosity. And if our shear stress is constant, then this du over dy will then just turn into u over L, right? And that signifies that it is constant. Okay, and viscosity is in Pascal seconds. So Newtonian fluids are where shear stress is directly proportional to shear rate. So if you put shear rate in the x-axis and you put shear stress in the y-axis, shear stress is going to respond to changes in shear rate. So Newtonian fluids describe fluids that are even in property, so they don't have any suspended particles. So these are things like water, like air, oil would be one of them, alcohol as well. And saying that their relationship is directly proportional, we know that it has a linear plot, right? And that is reflected in this model here. So if our du over dy, if our shear rate is positive, then we're going to get a positive slope. And if it's negative, we're going to get a negative slope. So in this case, we have positive slopes. And we see that the more viscosity our liquids have, the steeper the slope. So I'm going to write that down. So T, steeper slope. So that means there's going to be more shear stress per shear rate. So more shear stress per shear rate. Okay. So oil is thicker than water, and water is thicker than air. So it makes sense that air would have this most shallow slope, and oil would have the highest slope. So viscosity of liquids decreases with temperature. So if you're to take, I'm trying to think, sorry. If you took honey and you watered it down and you heated it up, then you would realize that as you added heat, then the viscosity would decrease and become more liquid and less viscous. And temperature dependence of a liquid can be expressed using this equation here. So this is our log viscosity equals some parameter, some constant A over our temperature plus some constant B. So we'll be using that equation to calculate some values. And now we're going to talk about power law of fluids. So we can use this relationship to describe our shear stress and how our shear rate are related. So if this is a plot of that equation, so as tau equals k, the absolute value of our shear rate to the power of n, because this is a linear plot, we could expect our n to just be to the power of 1. So that would just produce a graph that is in the form of y equals m, where m is our k, x. And we know that to be a linear plot, so that's why we expect our non-Newtonian fluids to look like that. So n is our flow behavior. So flow behavior, in this case, if it's greater than 1, it's dilatant. Let me rephrase that. So if n is equal to 1, if a linear plot, and this is Newtonian fluid, which is what our graph above represented, right? And we also have this new model, which is for apparent viscosity. And that can be represented by K times, so some constant K, times our shear rate to the power of n minus 1. So there's two types of power law fluids depending on the value of n. If you have n is greater than 1, you have a dilatant fluid. So if we were to plot our shear rate and our shear stress, dilatant with n greater than 1 would be, so apparent viscosity increases with shear rate. This plot would look like this. So it would curve up. Sorry, I'll draw that a little better. So it'll curve up like that. And for our pseudoplastic, so if n is smaller than 1, then you'll get a plot that looks like this. Right? So it'll start with a steady curve, and then it will begin to flatten out. So I'm going to switch these around so I can draw them a little better. This is our pseudoplastic and our dilatant. All right. And if we were to draw our last plot for a Newtonian fluid, we already know that looks like a linear plot, like this. N is equal to 1. Right, and the slope of it just depends on that constant k in the coefficient, and that will dictate how steep the slope is. Okay, so we're going to talk about steady incompressible flow. So if we have a non-even shaped, body that it's flowing through, then we want our rate of our mass in to equal our rate of our mass out. So this is similar to our material balance questions when we have a steady flow rate. So the rate of the mass in is represented by this equation here. So this is the area of our first port of entry. Right, so that would be A1. The velocity at this point, as well as the density at that point. And we want it to equal our area of our second port, so our port of exit, times the velocity there. But notice that our property of density remains the same, because as long as you're not introducing any new fluids, the density remains the same, because we're working with the same liquid. So we're going to talk about some other ways to describe our velocity. So our velocity at 1 can be described as our volumetric flow rate, which is given by meters cubed per second, over our area 1. And same can be said for the velocity of our second one, where we exit. All right, so we're going to go through some questions that help us solve for these values. And if you have steady, incompressible, inviscid flow, so that means we're not working with viscous fluids, the total mechanical energy is constant. So we're going to work with this model called Bernoulli's equation. And total mechanical energy takes into account 3 different kinds of energy. We have flow energy, potential energy, and kinetic energy. So we need separate equations that represent each one, where the flow energy per unit mass is pressure over rho, so that is this first part here. So this is flow energy. Then we have potential energy per unit mass, which is our height times our gravity. And finally, we have our kinetic energy. It's 1 over 2 velocity squared, where our average velocity is our volumetric flow rate over our area. So we want all of these values from our first point to equal the same properties in our second point, right? So in our second half, we also have flow energy, potential energy, and kinetic energy. So this is Bernoulli's equation. So basically just states that the total mechanical energy is the addition of all of these, and it's going to be streamlined between points 1 and 2, so they are going to be equal on both sides. Okay, and finally, we're going to talk about Reynolds number. So Reynolds number is a unitless number that we use to help us define properties of our liquid. So yeah, if we had flow of a liquid, if we added dye to this flow, if it were a laminar flow, the dye would not be disturbed. It would stay streamlined and would follow the path of the fluid and not get mixed. However, if it's turbulent flow, then the dye would get mixed. So laminar flow, you can kind of, I guess, picture it as like flow from a hose. So if you've ever used a hose and the water coming out of it looks as if it were not moving, it looks still, that would be described as laminar flow. But if you turn up the pressure of the water a bit, you might find that it's turbulent, the water is spurting a bit more, so that would be our turbulent flow. So there's going to be this model to represent our Reynolds number. And the value we get for Reynolds number is going to be a constant, right? Because all of our units are going to cancel out because this is a unitless constant. And if our Reynolds number is less than 2,100, it is laminar flow. And if it is greater than 4,000, it is going to be turbulent flow. So we have a couple things represented here. We have the diameter of the pipe. We have our average velocity times our density of our fluid over our viscosity. And this is the equation we're going to be using to help us solve for these kinds of problems. So we're going to go through an example in a couple seconds, and we're going to cover these properties of fluid using what we learned from these few slides. So in this example problem, we are going to be using data to help us find different parameters for our power law. And we want to find different values of it to describe shear rate and apparent viscosity. Okay, so what we are going to do, we're going to write out our equation for our power law. So this is tau, our shear stress, times K. And this is our shear rate to some power n. So we need to find for K and n. So find K and n. So this process is quite similar to what we did for our correlating equations that we used for our Clapeyron equations from our previous video. I'm just going to highlight these two data sets. We're going to use them here. So if I were to rewrite our value for, so if I were to rewrite this equation, I could add a log tau. Then when I add a log to this side, this brings our n down, and this is our log of K and du dy. And I'm going to rewrite this right half as, so using our log rules, so this is log K. Since we're using multiplication, this becomes plus in our log rules, plus log of our shear rate, and our exponent comes down. So our exponent n comes down, and this is log our shear rate value. So what I'm going to do, I am going to take this equation and let's plug in the values for set 1. For set 1, we're going to do log of our tau, so this is 62.3, equals log k plus n log, and this is 25. So this becomes, this 1.79 equals log k plus n, and this is log 25, and this is 1.39. 8. Okay, so that is our first one using set 1. And when we use set 2, so this is log 50, log of 81.9 plus log k plus n log 50. And this becomes, so it's log 81.9, so that's 1.9. Equals log k, and this is plus n, and log of 50 is 1.69. Just going to put 1.7. Okay, so now we have two equations and we have two unknowns. We have to relate these equations somehow to solve for one unknown. So what if we did this? So what if we took our 1.79 equals log k plus n 1.4, just going to round that up. And what if we subtracted this? Actually, what if we took our green one and subtracted by that? Sorry, let me write out my steps. So this is step A and step B. Now we can find for our n, because our log k's are going to cancel out. And then we have 1.91 minus 1.79, and this is 0.12. 0.12, and this is 1.7 minus 4, and this is 0.3. So if we just take our 0.12 and divide by our 0.3, find that our n is equal to 0.4. N is less than 1, so that means we have a pseudoplastic behavior. So let me circle this. N is equal to 0.4. And now we're going to plug this back in. So we're going to plug it into any of our equations to find what log k is equal to. So I'm just going to use equation 2. So we have 1.91 equals log k plus, now we know what n is, we have 0.4. Times 1.7. Okay, we get 1.91. Then we're going to subtract what 0.4 times 1.7 is. And our log of k is equal to 1.23. And by log rules, this is log base 10, so we can get k is equal to 10 to the power of 1.23, which is equal to 16.98, or about 17. Okay, so now that we've solved for n and k, then we can just write this final answer as tau equals 16.98 shear rate to the power of 0.4 for this specific scenario. This is our final answer. Sorry it's a bit messy, don't have much room to write. Okay, and use this relationship to estimate the shear stress at a rate of 40 inverse seconds. So we have our relationship, so we want to find shear stress, so that's our tau, so we have 16.98. And it wants our shear rate to be 40, 0.4. This is times 40 to the power of 0.4, and this is equal to 74.27 Pascal seconds. And finally, we want to find our apparent viscosity, which is given by mu is equal to tau, our shear stress over our shear rate. This is equal to, so we found what our tau is. Then we know our shear rate is going to be 40. And this is just equal to 1.856 Pascal seconds. Sorry, I made a mistake. This unit is meant to only be pascals. Okay, so that's just a quick example to go through some of the properties of our fluids, specifically relating more to power law. You're going to be using power law a lot. This was a shorter video. In the next unit, we'll go into more depth. So in chapter 8 of this content, we'll talk a little bit more about this kind of motion as well as Reynolds number. So yeah, stay tuned for the next video. We'll go into more depth. This was just a nice sort of introduction to some basic concepts that you'll be needing for this unit. All right, so I'll see you in the next one. Hope this helped, and thanks for watching.